Hello everyone, my name is Tarana Vidya and today I'm going to talk about a very interesting topic called as quantum key distribution or QKD for short. My aim is to explain it in a simple and clear way so that even someone new to the subject can understand it. We all know that in today's world, keeping our data safe is very important. Quantum key distribution is a modern and advanced way to secure information using the principles of quantum physics. So, in this presentation, we'll see what QKD is. So, before we start, let me give you a quick idea of what we'll cover in this presentation. First, we'll see what quantum key distribution actually is. Then, we'll compare it with the traditional methods of security so you can see why QKD is special. Next, we'll look at the working process of QKD to understand how it actually functions. After that, we'll discuss the BB84 protocol, which is one of the most famous protocols used in QKD. We will then explore the advantages and disadvantages of QKD to know its strengths and challenges. Finally, we'll look at some of the real world applications of QKD and what the future of this technology might look like. So, by the end of this session, you'll have a clear understanding of what quantum key distribution is from the basics to the applications. So now let us start with the basic question. What is quantum key distribution or QKD? In simple words, QKD is a way to share secret keys between two people securely. A key here means a secret code that is used to lock and unlock our data. The special thing about QKD is that it uses the rules of quantum mechanics, the signs of very small particles called as photons, to protect the secret key. So now, why is it better than the traditional method? In normal cryptography, security depends on solving very tough mathematical problems. If someone has a powerful enough computer, there's always a chance that they can break it. But in QKD, security depends on the laws of physics. Quantum mechanics says that if anyone tries to look at the secret key while it's being sent, the particles carrying the key will change their state. This means the sender and the receiver will immediately know that someone is spying, so they can immediately stop their communication. Also, QKD gives something what we call as forward secrecy. Even if someone finds out the future keys, all the old keys remain safe. So now let us understand how the quantum key distribution actually works. Imagine we have two people, Alice and Bob. Alice is the sender, the one who wants to send the secret key, and Bob is the receiver, the one who needs to get the key safely. And then there is an eavesdropper, Eve, the person who tries to spy on the communication. The goal is simple. Alice and Bob wants to share a secret key even if Eve is listening. QKD makes this possible because of strange properties of quantum particles. If Eve tries to listen in, the particles carrying the secret key will change the state, and Alice and Bob will immediately know that there is a security breach. We'll know this using the five simple steps. We'll look at the five simple steps that will explain the entire process very clearly. So this slide gives an overview of the steps in the quantum key distribution or QKD. The goal is simple. Two people, Alice and Bob, want to share a secret key securely so that they can encrypt their messages. But they are using quantum mechanics instead of classical methods. Quantum properties like the behavior of photons help them make the process secure. The five main steps are key generation, measurement, key agreement, eavesdropper detection, final secret key. So key generation. First, Alice wants to share a secret key with Bob. To do this, she uses tiny particles of light called as photons to carry the information. Each photon is prepared randomly in different directions, like horizontal, vertical, or diagonal. This randomness makes it impossible for anyone to guess the key in advance. Measurement. Now, Bob receives these photons. But here's the twist. Bob doesn't know the directions Elias used, so he randomly chooses some orientations to measure them. Sometimes his choice matches with that of Elias and he gets the right information, either a 0 or a 1. When it doesn't match, the result is meaningless and they will throw away those bits later. Key agreement. After this, Elise and Bob talk over a normal public channel. They don't reveal the actual keywords. They only compare the orientations they used. Whenever the choices match, those bits are kept. The mismatched bits are discarded. The remaining bits form what we call as a raw key or the shift key. eavesdropper detection. Now, what if someone like Eve is secretly listening? In quantum physics, if Eve is trying to measure the photons, she changes the state. This creates errors in the key. Alice and Bob compare a small part of the key to check the error rate. If it's too high, they know Eve was spying and they throw away the entire key. So final secret key. Finally, after removing all the errors and correcting the noises, the remaining bits form a perfectly secret key. This key is now used for encryption, which is used for making the messages completely secure and unbreakable. Now let us talk about the BB84 protocol, which is one of the most famous methods in quantum cryptography. This protocol was created in 1984 by Bennett and Bresard, and that's why it is called as BB84. The main idea is that it allows two people, usually called as allies, the sender, and the Bob, that is the receiver, to share a secret key securely. What's important here is that they can do this even over an insecure channel, where there might be an eavesdropper often called as Eve. The key point about BB84 is that it uses quantum properties of light particles called photons. Because of the quantum mechanics, if someone tries to observe or measure these photons, it automatically changes their state. This means that any attempt of eavesdropping can actually be detected. In this picture, you can see a light sending photons in different bases. These bases are different ways of encoding the bits. Bob then receives them and measures them. If Eve tries to intercept her measurements, it will disturb the photons. And Elias and Bob will know that something is wrong. So BB84 protocol is special because it's the first practical example of how quantum mechanics can help us achieve secure communication in the future. The first step in the BB84 protocol is that the sender, that is Alice, requests a set of photons or qubits to be sent to the receiver or Bob. Qubits contain all the information about the key. Then Alice generates two random sequences of the same length, a random sequence of the bit values, that is zeros and ones, and a random sequence of the bases, that is Z or X. Then Alice generates qubits in the quantum state using the combination of the bases and the bit values. If the basis is Z and the bit value is 0, then polarization sent would be a 0. Similarly, if the basis is Z and the bit value is 1, then the polarization sent would be 1. If the basis is X and the bit value is 0, then the polarization sent would be a positive sign, and a bit value is 1, then the polarization sent would be a negative sign. The measurement made in each basis has only two possible outcomes, that is, if the base is Z, we have only two possible outcomes, that is 0 and 1. And the base is X, we have only two possible outcomes, that is positive or negative sign. Let us see this with the help of an example. These are the random bit values generated by Alice, and these are the random basis values generated by the Alice. Now let us find the polarization sent. So it is given that the bit value is 0 and the basis is X. So basis is X, the bit value is 0, so it would be a positive sign. The polarization sent would be a positive sign. Similarly, the bit value is 1 and the basis is X. The polarization sent would be a negative sign. The bit value is 0 and basis is Z. Bit value is 0, basis is Z. The polarization sent would be a 0. 0 and Z. 0. 1, 1 and Z. 1 and Z would be a 1. 1 and X. 1 and X would be a negative sign. 0 and Z. 0 and Z. The polarization sent would be a 0 and so on. So, this is the polarization sent by Alice to Bob. Second step of the BB84 protocol is that the receiver measures the photons. Bob doesn't know which basis was used by Alice, so he randomly chooses a basis to measure each photon or the qubit. If Bob's basis matches with that of Alice, then it is a correct bit. If the Bob's basis differs from that of Alice, then it is a random bit. Let us see this with the help of an example. Let this be the Alice's basis and this be the Bob's basis. Here if we see Alice's basis matches with that of Bob's basis, so it is a correct bit. Here there is a mismatch of the basis, so it is a random bit. There is a mismatch of the basis, so it is a random bit. So here if we see Z and Z, that it is matching, so it is a correct bit. Again there is a match, so it is a correct bit. Again there is a match, it is a correct bit. Here there is a mismatch mismatch of bases. That is, here we have Z and here we have X. So there is a mismatch of bases. So this is a random bit, and so on. So this is how Bob measures the photons or the qubits sent by the allies or the receiver. The third step in the BB84 protocol is the basis announcement. The sender, that is allies, and the receiver, that is Bob, publicly compare the bases used, that is either through a phone call or the internet. Here we do not compare the actual bits, only the bases are being compared. They only keep the bases that were matched. These are called as the shift keys. The other bits that were mismatched, that is, we saw random bits in the previous step, are then discarded. This is how the basis comparison is done in the third step of the BB84 protocol. The fourth step of the BB84 protocol is eavesdropping detection. Eavesdropping detection is one of the major advantages of the quantum key distribution concept. Here, the sender, that is the allies, and the receiver, that is the Bob, randomly choose some bits from the shifted key and then they compare publicly either through the internet or through a phone call. If the error rate is low, then they proceed to the next step. It means that the eavesdropper is absent. If the error rate is high, then the eavesdropper is present. How does this work? If the eavesdropper, that is the Eve, is measuring the photons, there is a change in the state of the photons or the qubits due to quantum mechanics, especially the Heisenberg uncertainty principle. This introduces the errors which are then detectable with the sender, that is the allies, and the receiver, that is the Bob. This is how we do eavesdropping detection using BB84 protocol. The fifth and the final step of the BB84 protocol is key dilution. After removing all the errors and the mismatched bits, the remaining bits form the secret key. So this secret key is then used for the encryption algorithms like one-time pad or AES. Now let us look at the advantages and disadvantages of quantum key distribution or QKD. Starting with the advantages, the biggest benefit is the unbreakable security. Unlike traditional methods that depend on mathematics, here security is based on the laws of physics, which makes it much more stronger. Next, we have the eavesdropping detection. If anyone tries to intercept the communication, the quantum state changes, and both the sender and the receiver will immediately know. QKD is also considered as future-proof because even powerful quantum computers cannot break it. This is very important since quantum computers can easily crack many traditional encryption algorithms. Another plus point is the key refreshing. The secret keys can be updated frequently, which keeps the communication extra secure. But of course, QKD is also having some disadvantages. The first is the high cost. The technology requires special equipment like photons detectors and photon sources, which are very expensive. There is also a distance limitation. QKD works well over a shorter distances. For long distances, we need additional devices called as quantum repeaters. Another challenge is the infrastructure need. To use QKD, we require fiber optic cables or satellite-based systems, which makes it hard to set up everywhere. Finally, QKD is not widely deployed. It is still in the research stage, and real-world applications are limited right now. So while QKD is very powerful and secure, the practical uses still face challenges like cost and scalability. So to conclude, let us see the real-world applications. To conclude, let us see the real-world applications and the future outlooks of the quantum key distribution. In terms of real-world applications, it is used in the banking and the financial sector. QKD can make the money transfers and the financial transactions extremely secure. In government and defense, it can protect the top secret communications from the cyber attacks. In the healthcare industry, QKD can be used for the safe transfer of the medical records. And in the cloud security, it helps in protecting the sensitive information stored on the cloud platforms from the hackers. Now, looking at the future outlook, we may soon see the integration of QKD with the quantum internet, which will give us the secure global communication networks. Another focus is the cost reduction, making this technology cheaper and easier to use for the organizations. QKD also plays a big role in 5G and IoT security, where billions of devices are connected and need strong protection. And finally, there's the space-based QKD, where satellites will be used to secure communication across the continents. So in summary, quantum key distribution is seen as the future of the cybersecurity. It provides unbreakable security based on the laws of physics, and it is especially important for protecting against future quantum computer attacks. Even though there are some challenges, QKD is expected to become one of the more common and mainstream in the coming years. So these are the resources which are used to develop the PPT and the video content. Thank you for watching my presentation. I hope this helped you to understand the basics of quantum key distributions, its advantages, disadvantages, and the future application. Cybersecurity is becoming more important every day, and technologies like QKD will play a big role in keeping our information safe. Once again, thank you for your time and attention.